Our speaker this evening has over 25 years designing and developing high-performance web-scale infrastructure, during which time he was a lead engineer at Novell. Please welcome the CTO and co-founder of Aerospike, Brian Bulkowski.
Thank you. Thanks for coming out, and thank you, Eric, for your usual high-energy starting position. Hopefully you feel good about that. Was anyone at Burning Man last week? Anyone? I was, and I'm still having trouble adjusting, so if anything goes wrong during this talk, you know, it's because you're all kind of still floating a little bit. So. Okay, what I'm here to talk to you about today, the reason many of you, I'm sure, are here, is to tell the story of Aerospike and AppNexus. I've done a lot of the Database Month talks. We've talked theoretically about how to do analytics on an operational database. I've talked about futures and flash memory. Last time out, I think we had a guy from SanDisk who gave a really interesting roadmap about NAND. We've talked about Docker containers. But right now, we just want to talk about what really happened at AppNexus. And I would say how many of you know AppNexus, but I'm sure it's all of you, right? Yeah, okay, so some of you are tired from Eric's thing, raising your hand. So this talk was originally given by Christopher Bowman. And if you want to hear him tell this whole story in his own words, just go to our website, our webinar link, and look for the operational techniques and scaling, basically the same talk, which he gave just a couple weeks ago. And I'm sorry, it is a password protected. You're going to give your email address, and someone from Aerospike might actually call you. I apologize, but it is a pretty good talk and a pretty good webinar, although you're going to hear it here. Chris Bowman, if any of you know him, he's a really interesting guy. He's been at AppNexus since pretty much the beginning. He's now responsible for pretty much all of the database groups, both operational and analytic. He also consults with all of the new data initiatives within the company, and he's been awarded there at AppNexus a few times. So if you don't believe me, go listen to him say all this stuff in his own words. So let's talk for a minute about what AppNexus is. AppNexus is a platform. When Brian O'Kelly and Mike Nolet started the company, their goal, their first idea was actually to go compete with Amazon Cloud. That was their very first business idea. And that's why this is an AppNexus. It's where apps come together in one data center to exchange information for a variety of business purposes. When he actually tried to get that idea funded, they said, start small, start with one industry, and the application of that one industry before going and taking on all of Amazon Cloud, which turned out to be a pretty good bet. And so Brian, having come out of, I think it was a DoubleClick, and out of the sale to Yahoo, he said, okay, so I know the ad industry, and the ad industry benefits from having a lot of impressions, a lot of ads, and a lot of bidders. And what Brian's told me is, he said, you know, the Google Ad Exchange is very, very powerful and very interesting and simple to use, but it's a black box. As an advertiser, as someone who is trying to place ads, you don't know what their algorithms are. You don't know if you're getting the best price. And so he always wanted to shine a light on that entire industry and create an open platform where a variety of companies could come, store their data, interact, and see a great deal of impressions coming through and bid on them, giving the best price for content owners as well as the best reach for advertisers. So that was the entire idea of AppNexus. When they first, the requirements then need to have a lot of data because you have all of these different companies and all of these different advertisers storing personalized information that only they have or only they have access to, as well as AppNexus's own information. That turned out to be a key portion of their business and business plan. So when Mike Nolet originally came and talked to me and Srini, he said, it has to be flash. Because he had looked at the cost of DRAM and the amount that advertisers were willing to pay in terms of the amount stored per data, and said we can't do it with RAM. these guys won't pay us enough to store their data and then use it for us to make a profit. He also knew that Google was using RAM at the time, and he knew he was competing against Google. They wanted an unfair advantage to be able to take on a leading edge of hardware in order to get a jump on Google in order to do that. So this one component that we'll talk about today of the operational data store really ended up being one of the most important portions of all of AppNexus's business plan, as well as their technology stack. Now, AppNexus has had a very interesting growth path. Those of you who have been following them, their load has doubled approximately every 9 to 12 months for 6 years. So that's pretty much hypergrowth, now putting them at the same level of scale as an advertising system as Google, Yahoo, or other major industry players. Some of Aerospike's other customers include Trade Desk, if you know them. They filed for IPO last week, and we're very, very happy to have supported them. Rubicon, AOL, Yahoo's video subsystem all use Aerospike in the same kind of way that we're going to describe here. But AppNexus was our first customer. So part of the story is that, well, let's go into what the AppNexus architecture is for a moment. So on the, and this isn't my slide. I probably would have done something a little less stick figure. It's a true slide, which is they have at AppNexus this concept of the impression bus. An impression in advertising is a chance to place an ad. It's basically a blank space on a web page. And so a web request comes in, that's the person here, and suddenly now the impression bus says, hey, we've got a place to put an ad, an impression. We need to now farm that out to all of the individual companies inside the AppNexus and see what they're all going to bid. This was really the beginning of real-time bidding as we know it today. Now, as we know, AppNexus participates now in many auctions, many different types. They do programmatic premium, they do a variety of programmatic. But at the time, it was really all about leveraging remnant inventory, which was fairly cheap at the time because things like real-time bidding didn't exist. And AppNexus pioneered that. So you get the impression coming in, and it has a variety of metadata. It has a series of cookies. It has user-placed cookies, cookies placed by third parties. It has AppNexus's own cookie. And it also has things like the size of the ad and what you're allowed to place. Are you allowed to place video? Are you allowed to have sound? A variety of different metadata tags, as well as things like the user agent. All of that is available on the impression bus to the bidders. The very first part of this step in the impression bus is actually to take the external cookie set and map it to an internal AppNexus cookie. They call that the mapper or cookie map, and it's a common part, a reverse index of most bidding systems. AppNexus, along with most of our customers, does that with a RAM-based in-memory cluster as opposed to a flash cluster. Then what happens once they get that internal ID is they then look up a larger piece of user data that does include information not just of recent behavior placed by AppNexus, but also by third parties. All of that information is then farmed out to the bidders, and then they use that to make their decision in a typical real-time bidding system. So this is a little bit of a classic architecture, and Brian and Mike and those guys knew it before coming into AppNexus. And they knew that this component was going to require a fast, reliable key-value store. Because if you don't have any information about a user, what are you going to bid? You don't have any information. And so this piece going down means that the system is essentially non-operational. Sure, you can still place ads, but you can't actually bid with any kind of regularity. And that's what drives the requirement for having extraordinarily high uptime. One of the most important parts about AppNexus compared to some other systems like this, remember, these are outside companies. So what they impressed upon us mightily at the very beginning of the engagement was, if this goes down, it's not just the amount of money you lose in 5 minutes or 10 minutes. It's the AppNexus brand. And one thing you might know about AppNexus from the period of 2012 through 2014 is they were known as having the rock-solid platform. And when other folks were having outages and going down and having trouble dealing with scale, AppNexus was always up. And all you have to do as an advertiser is have one or two campaigns that are suffering from outages when another platform is doing really well and able to serve ads to start thinking about switching. So that was a key component of their choice in this portion of the architecture was uptime. Not just for money, but simply for brand. So the system that they have has scaled at approximately this level over the years. So when they first approached us in 2010, they said we need about 1 billion objects. That's grown to about in 2016 to about 50 billion objects, all of which are available in millisecond latency. They needed no maintenance windows, and they needed roughly, they came in with this, and they're currently at this kind of load. So that's pretty staggering growth. What's hidden behind these numbers is the kind of peak load that they can handle. I can even look at these numbers now and say, well, 2 million a second? I mean, that's not that great. We've seen things, we've published numbers, for example, on Intel Flash of 1 million transactions per second with a single server. And they have a lot more than one server at AppNexus. That's because they need to be able to handle extra load, they need to be able to handle peaks. What also happened in 2014, those of you who are familiar with the ad industry, is that there was a lot more fraud within the advertising system in general. So during 2014, AppNexus was actually at about 5 million transactions per second before they went and cut back and put much more advanced fraud algorithms to remove basically bogus impressions. Because there were a lot of people out there gaming the system, they had false impressions, and they were getting paid for impressions that didn't exist. And AppNexus pretty much put a stop to that on their network. They've got some great algorithms for it. But they were at about 5 million in 2014. The other thing to remember is the 2x load that happens on certain days. I remember Brian O'Kelly talking at one of the AppNexus summits a few years ago, and he said, look, we all gear up for Black Friday and the time right around Christmas. And he said, you don't know what happened during the last presidential election. Last presidential election, we saw a peak higher than we had in any shopping day across the Christmas season. It turned out that year that that was the first year that the presidential campaigns started doing geographic targeting based on real-time exit polls during the course of the day. So they actually knew precinct by precinct what was in flight, what mattered, and started pounding those specific areas with advertising and thus driving up prices within it. All of that is capable within the advertising system today. It was pioneered about 4 years ago in the presidential election, and boy did they have a huge spike over at AppNexus, and they handled it. So these numbers to me honestly look a little low, but they shouldn't look low. I mean, those are real operational numbers. That's what you see on their servers intraday during the course of an average week then. So then Brian first came to us. Let me tell you the story of how the engagement happened. Myself and Srini, my co-founder, we'd written a prototype of this key value store. My co-founder Srini had recently come out of Yahoo, and he had scaled Yahoo Go, which was their mobile effort, in 2008. Those of you who remember it, I'm surprised because it kind of sank without a trace, honestly. But it was a great product. It was debuted with the very first iPhone with Steve Jobs on stage showing push email. That was my co-founder Srini's product. And he knew the value of keeping initial operational queries simple. And that's really one of the, a lot of people ask me at Aerospike, what do I give up for all of this performance? And it's actually kind of simple. No distributed range queries. Okay? Focus on key value. key value, the thing that should be fast and should be order one and is embarrassingly parallel, you better be able to do that really, really fast. And build your architecture around reliable primary key accesses. Now, Aerospike has a distributed range query. Aerospike does allow you to query across the entire cluster. It has a system of filters, user-defined functions, geospatial queries, all of that stuff. But the fact is, when you're building at this scale, you really need to keep to direct key value lookups. You may do a batch of them. We have a lot of people doing analytics. For example, fraud detection is often about getting individual IP addresses and the recent behavior in them. But really, you have to focus on that key value lookup in order to maintain this kind of speed and performance. And the guys at AppNexus knew this, and Brian in particular went and looked through a lot of the different software that was available at the time, there wasn't that much, that focused on key value lookups. So they knew that they wanted to do Flash, and they knew they needed a key value store service. What they did was they found a company called Schooner. Schooner's actually was located kind of near my house on Willow Road. It's about halfway between my house and Facebook in Menlo Park. And those guys had taken a hardware appliance approach and basically put memcache and put it on flash storage using memmap and crammed the whole thing into a single appliance, which isn't a terrible idea. Except they didn't do a lot, and they promised Brian was even on the board of directors as I understood, and they promised him they would do clustering. Because without clustering and scale out, well, you know, you hit the limit of that first box, and then where are you? So they promised all of that stuff, but ended up not being able to deliver because distributed systems are kind of hard and much, much harder than simply, you know, tossing some flash and an open source copy of memcache into a box. So what happened was they hit that limit of that individual box and then started talking to a few of the players who were building this kind of stuff. Myself and my co-founder at that point had built a prototype, and we were trying to take it around to a lot of the folks in Silicon Valley who were building internet scale services and getting them interested in using it. For example, I remember we went to Salesforce. Salesforce really just uses Oracle as a glorified key value store, uses very little of the database functionality. We thought it would be a great idea for Salesforce to ditch Oracle and switch to Aerospike, even though we were, you know, two guys. So that was a little crazy of us, but you know, it takes a little bit of craziness to try to start a database company. We went to Second Life. If you remember Second Life, they're still around, the gaming company. They were having trouble with scale. We went to PayPal because their coherence cache in front of their main Oracle system was suffering a lot of outages at that time, and we had some friends over there. And in general, people weren't desperate enough to try to bet their entire company on two guys, even, you know, two guys with PhDs in databases, my co-founder who worked in IBM Aldenton Labs, et cetera, and myself with my pedigree. It was still a little much for them. But one day we were sitting at Srini's house trying to figure out what to do, and Brian O'Kelly calls up and he goes, hey Brian, you still working on that database? And I'm like, oh yeah, Brian, it's going great, you know, everything's great. And he said, well, things aren't so great here, because the company, the Schooner product that we picked instead of you has tapped out, it's hit its limits of scale, and we need something that is what you guys have, all software, flash-based, and clustered. Can you guys come in and basically put it all in? The benefits of Flash can be shown right here. This isn't the AppNexus deployment, it's a different customer. But just to show you the way that the AppNexus guys were thinking about it even at the time, they essentially saw this 10x in DRAM versus NAND flash. And the interesting part about this analysis is your database will still be just about as fast. The overhead of doing a read from NAND is only about 70 microseconds. Sometimes with some new devices it's about 10 microseconds. A lot of that is OS overhead, but some of it is also media. Media ends up being about 10 of that microseconds. If you know TCP and TCP ping times, they might easily be 100 microseconds to 150 to 200 microseconds, even on a well-functioning network. This means you're not going to pay a lot in performance for using NAND flash, you gain an amazing difference in price. And this is a price with some guesstimates about power, maintenance. I prefer actually looking at Amazon's prices. If you just go to Amazon, because that's an all-in price, right? It includes wear of the SSDs, it includes data centers, and it even includes the pricing power that Amazon has in buying for its customers. Go look at the price of a gigabyte with an Amazon i2 instance versus DRAM, even with their high RAM instances, and you'll see it's about 10 to 1. And it's maintained a 10 to 1 difference, even over time. So when these guys wanted to switch from Schooner, which was also Flash-based, over to Aerospike, the first thing that they had to do was do a side-by-side trial, because you already saw how critical this was to their business. Downtime is, uptime is everything, and downtime is crucial. So what they did at first was they said, we're going to run a side-by-side test. We're going to start with an Aerospike cluster. They had us size it, and they even ran it on virtual machines, because they didn't know if it was really going to work or not. They took 8 virtual machines, and it was something like a quarter of their load, and for about a week and a half, they just started writing to it. Just writes, just in order to make sure the writes were there, the data was correct compared to their reference system, before they actually started doing reads. And as this bullet point says, they ran that test, and there were a few issues. Any of you who has ever gone through taking brand new C code into production knows that there's going to be a few issues. So we had a couple of very exciting weeks here in New York, me and Srini at the old AppNexus office, and fixed a lot of issues in a hurry. After that, what happened was, I remember we were on a call with Mike Nolan, and we said, well, okay, so you guys have been in load test now for about 2 weeks. And we've got about another week and a half left on the load test. How are things going? What are your timeout rates? What are your simulations showing? And Mike said, oh, we've actually cut over to you 100% now, once they moved to bare metal. He said, we would be losing $10,000 a day if we stuck with our old system. So we moved over to you already, without warning us. So the test cluster very quickly turned into the actual bare metal production cluster, and they switched over, because one thing I love about dealing with people in advertising is they're very down to earth, very dollars and cents. They don't worry too much, especially at that time, about process, and they're really about finding a solution that works. And so that's what Mike ended up doing. So let's talk for a minute about how Aerospike actually does this. Think about Aerospike, as I mentioned, as a high-performance key-value store. The most important fact about key-value and distributed hash table is it has to be order 1, no matter what the data is. And you have to use the fact that these accesses are very, very parallel. And that's great, because Flash responds very well. NAND Flash responds extraordinarily well to what's called high queue depths and a huge amount of parallelism. This is one of the reasons why Flash and a key-value store is almost a match made in heaven for this. So what happens within Aerospike is that there's a set of clients. Each one of these clients is in native language. We support pretty much all the languages. And each one of them, once it connects to the cluster, is able to find out where all of the data is at any given time. So it reads and learns the current state of the distributed hash table. Once it has that, it uses essentially a form of micro-sharding, where we have a very large number of shards. And once you have a shard, you figure out where that server currently is. You have a queue of connections, and then you send that request directly to that server, and you get its answer. So there's no proxies involved, and it is automatically load balancing. In fact, if you try to use a load balancer with this, you're going to be in a world of hurt, because it really wants to know where all the data is. Now, let's say you lose a server. Within about 200 milliseconds, there will be a new Paxos leader election that will reorganize the servers and allow all of the servers to figure out who's gone, what parts of the data are gone. Well, if it's only one server, you probably have 2 to 3 copies of the data. You may have to do new master elections for some portions of the data. You may have to promote replicas for other portions of the data. For other portions of the data, everything's fine and it stays there. All of that happens, and clients are immediately updated within a second or two with the new locations of the data, new masters, etc. All of that happens without any maintenance, which is one thing that the AppNexus guys, and Brian in particular, when he was looking at the code, really appreciated. Because it's one thing to have a cluster that stays up, but when you have 2,000 bidder nodes, bidder processes, not physical machines, to try to go through when in 2 a.m. you've got some kind of a hardware fault and get these guys all reconfigured with new cluster sizes, that's kind of a monumental undertaking. And Srini and I, having lived through some of that with prior systems, knew that managing these clients and putting a lot of work into making these clients as seamless as possible was actually a lot of the hard work about making this a good operational system. So that's the one-hop to data node load balancers, and really a key part of the architecture. Now, another thing we realized early on was if you're running for high availability, you've got multiple data centers. There's not really, if you're just designing for a single data center, you're not really designing for high availability. So one thing that we built was a system of what we call XDR, or data center replication. In general, currently, the system can work in a multi-master mode, but I admit it's a little bit of a hack. Right now, a lot of our folks end up having either a single master, or they end up having each individual user key homed in a different geographical region. However, you can set up things like rings and star topologies that allow you to snap in and snap out data centers. One story from the guys at Exalate was Exalate uses a north, south, east, west topology in North America. And their data center provider in the west, essentially in Texas, their network was going south on a regular basis, and they were having a lot of outage problems. So they were able to snap a new data center into the ring. So I'll roll through this kind of quickly. So the interesting point about what Chris Bowman went through when he was scaling Aerospike and scaling the AppNexus operational system was simply adding more cluster nodes just became more and more of a problem. And this is the classic distributed system case where you add more nodes, you've got more failure points. So your system as a cluster starts failing more and more because every machine has its own failure rate, and that becomes higher and higher. So what they did was they ended up doing a scale out, but also a scale up strategy that was pretty unique. And folks at who use Aerospike end up using this strategy. And that's, I think, one of the takeaways from this talk is that scale out plus scale up is a pretty wonderful technology approach. So what happened was they started with their 8-node cluster in 2011, and then basically that rolled up to, is there a number here? About a 40-node cluster, right? So remember that curve there. So they got up to about a 40-node cluster, and that was the point where they started going, our failure rates are kind of high now. Every few weeks we have a node going out, we have to do maintenance, we got to do something about it. So what they found was that besides just doing scale out, they should also use scale up at the same time. So every 2 years, what they've been doing is forklift upgrades. They buy an entirely new cluster, they run it in parallel. I'll show you some slides on how that's done with Aerospike. They get all the data migrated into it, they decommission the old cluster. And they do that with zero downtime, zero maintenance window. That's kind of the cool part. So it's just kind of like, remember I told you the story about how we first started working with them? They had their old system, Schooner, and they had Aerospike. You take the old cluster, and it's got your reads and writes. You've got your new cluster with a lot fewer machines. You then set up that replication system that I talked about, so that all the writes that are hitting this machine are automatically getting forwarded to that. But it doesn't have all the data yet, right? It only has new data. After that, what you do is you take a backup of the old cluster and you restore it to the new cluster. You do that with a particular option that allows you, with Aerospike Restore, that says don't overwrite any data that's already there. right? So you've got your replication going, everything's fine, and then you do one of these backup restore dances. At that point, you can start doing reads against your new cluster, take a percentage of the load, make sure everything's okay, and then you can cut over. So these guys have done it, I think, 3 times, and they ended up with a system that is, at this point, actually using SATA. So a lot of my other talks talk about Flash. If we had a little more time today, I'd probably talk to you about it some more. But SATA is the base of their cluster currently, what I call wide SATA. So they've got these 2U chassis with 20 SATA drives in them. They do that for performance, but also for cost. SATA drives, when they chose this hardware a year and a half ago, were a lot cheaper than NVMe systems, the NVMe systems we have today. Since then, NVMe has dropped radically in price. And whether you choose NVMe or there's still SATA drives out there, depends on the amount of writes you're going to take, the durability you need, the price performance you want. There's sort of a whole trade-off. Everyone's got their own products in this area. So that's what, and we ended up doing a case study with Intel on it because it really showed that you could scale up NAND flash within a SATA system to a pretty high level. So one thing that Chris talked about during his talk was the responsiveness of Aerospike during this period. And anytime, any of you who have scaled up a system know that you're going to run into another problem right around the corner, whatever it is. And it's very hard for a vendor to test that. It's hard for a vendor to replicate the environment. We've never actually even had the size of hardware that AppNexus has today, or any of our major customers. We don't have a cluster the size of trade desks or Exalates, or really anyone else. We do a lot of simulations. We do a lot of work with cloud test dev, but that actually doesn't cover all the cases. You just get some weird cases. Like one war story right now, we're currently doing some work with a major West Coast retail auction site, and they're using us for a particular use case in Google Compute Engine. And Google Compute Engine's live migrate is somehow throwing weird network packets at us. We don't know why. And it's causing some problems and causing servers to crash. So we've got 3 engineers right now working on fixing it. We can't simulate it. None of our test environments show it. None of our test environments have shown it, even within Google Compute Engine system. We just can't, we can't reproduce it. So one thing that the AppNexus guys have been very happy about is we're there for them no matter what. And even though root cause is sometimes in the network, sometimes it's in the storage layer, sometimes it's in the Aerospike software, they really want to have someone to call who can actually sit down, work with them at a high level of scale, and try to solve their problems. In particular, there's 2 key improvements that we've made over the last few years that have really pushed higher and higher levels of scale and fixed some of their operational problems. So, thank you for sticking through the fire drill. Maybe we can open up to a few questions. In the back.
When you talk about scaling out versus up, for the basis of node failures, is that going to be bigger boxes versus more expensive plus boxes?
Bigger in speed. So the question was, is that scaling up to a more resilient box with multiple power supplies, et cetera, multiple NICs, or was it scaling up to a faster box? It was scaling up to a faster box. So they were already using dual NICs, bonded, multiple power supplies, et cetera, et cetera, et cetera. And yet still, with 50 servers, they would occasionally see outages, misconfigured switches, et cetera. So it was really about that process of going up to 50, 60, 70 servers, and then using Moore's law to go drop back down.
Right, so is that machine issue or a box or infrastructure operation? That doesn't sound like fun.
So the question is, why were they having so many failures?
These things happen. It was just a question.
Yeah.
Is it more from that one versus the other?
It wasn't wasn't usually our point to say to our customers, we think you could do things better, but often to just exist within the realities. So I'm not sure I can really comment on whether it was, some of it was hardware, but AppNexus has always been a stickler about using tier 1 VARs. It's not like they were using white box. I think they're a Dell shop, and they've always stuck to pretty straight down the line hardware. So it wasn't that they were really cutting corners on that side either. I think it's just more the reality of a modern deployment. Sir.
Can you give an overview of your licensing of the product?
Sure. Overview of the licensing. We have an open source version. The open source version is obviously not limited in size, scale, speed, or anything like that. But it does have a few missing scalability features. So for example, the two features that Chris pointed out as being really important for large-scale deployments, which is faster restarts using essentially persistent RAM, as well as a way of synchronizing the clusters that's much faster. Those are only in the Enterprise Edition. So you can get started with the open source version. It is AGPL, so just like MongoDB, say what you like about AGPL, we can have that discussion at some point. And then there's basically this proprietary license version. The enterprise version we sell by data size, which makes us somewhat unique among a lot of the distributed systems guys. Most distributed systems guys charge by nodes. However, early on, I really wanted not to do that because there's a number of business problems that occur. One is, imagine what I was just saying about getting to a 50, 60, 70 node cluster and then dropping down to 12. What am I going to tell my board of directors? Oh, we suffered a 4x, our license revenue went down a factor of 4 because our customer used more efficient hardware. No, they would kill me, right? And yet anyone who does node-based licensing is always fighting against Moore's law. As machines get faster, you essentially get less license revenue from the same workload. Whereas data is always growing. But it's not a perfect license model because TPS is really a big part of, and transactions per second is really a huge part of what Aerospike is. That's not in our pricing model. It's just data volume. So that means if you have a small amount of data but a huge amount of performance, you're probably going to make out like a bandit, and your licensing costs for us are going to be kind of low. And we know that. So you try to sort of all have it come out in the wash.
I wonder about this scenario that you described about data replication in cluster. So first you enable basically online replication, replicates on the current transaction. And then on top of it you explore previous data. So okay, you're saying you have an option to not override and so on. But what about deletions? How this is handled?
Deletions. Deletions essentially count as a write in some sense, and then they also don't count as a write. So let me go back separately. Most of our ad tech customers don't ever delete any data. They count on expiration. So they use what I call a run full methodology, where they bought all of this storage. They want to use all of it. They don't want any of it to go to waste. And they simply want the least recently used or written data to time out. So they never do an explicit delete. So for that reason, having a little bit of, having this kind of methodology works okay for them because they don't delete. Now in the case of doing an explicit delete, Aerospike has a coming feature where we're going to write a tombstone. Tombstones will be replicated and thus will work across XDR in this system just as well. And the fact that there will be a delete persists in the destination cluster, and thus when you try to write on top of it, it knows that the data is not there. And you need tombstones in order to do that and to properly act in a case of explicit deletes. And the upcoming feature does all of that correctly.
And you will have tombstones for kind of forever? You will not do compaction or anything?
Our system for of course we have a system for removing tombstones. If you don't remove tombstones, you get to the problem of, the graveyard's full.
Right.
Where are you going to put the bodies? So of course we have a system for removing tombstones. We call it the Tomb Raider. Yes?
Any chance to see Aerospike among Google or AWS ecosystems?
Yeah, we see a lot of it. 40% of our paid users are in Amazon. Who uses it in Amazon? I'm pretty sure AOL does at this point. I think they moved. Yeah, a lot of folks are, is the sort of the short answer. DraftKings, King.com, I think, is one of the Google Compute Engine guys who use us. So a lot of folks do.
The question is, for example, Redis or Memcache, they kind of built into the AWS services. Any plans going there?
We built that a year ago. So we built Aerospike as a service. Aerospike as a service. So we call that Project Burrow, because that's a form of as. And we found the uptake was actually kind of low. We decided to actually put that on the shelf for a while, but we actually did have a managed service for a while. It was at aerospike.io. You could start up clusters, basically back up and restore them, have little database images, all that kind of stuff. But we found that we found the uptake was kind of low, and so we've shelved that.
When you do your consecutive writes, do you need to do the compactions at some point, even without deletes? You still need to do compactions,
of
like
course.
everybody else. So how do you handle that? I mean, when compactions are going, obviously the performance would suffer.
No. You do compactions as you go along, so the performance is the same at all times, but it's derated. So instead of what we do, as part of our methodology, is we have a defragmentation process that is actually working second by second to take partially full blocks and rewrite them as full blocks. So yeah, performance suffers during that time, but it's not a peak and a valley situation, it's constant.
And what's the percentage of this performance suffering versus if you don't do that?
It depends on how full your database is.
So let's say it's random writes. I mean, you write according to random keys. I mean, keys
But
are
it depends
random.
on how full your database is. It doesn't depend on as a percentage of performance. It depends on the percent full your database is. So for example, if your database is 50% full, for every write, you need to do another write to free up space, and you need to do, 2 writes and 1 read. 1 read to defragment, 2 reads to defragment a block, 1 to actually write the defragmented block, and then 1 to write the original data. So, but that's just math. Everyone has the same problem. To do 1 write, you have to do 2 writes and 2 reads.
And you do it on write. So you do the every compaction.
No, it's a background process.
No, right. But every write basically goes in that theoretical example to 2 writes and 1 read. It's not that you do it
in terms of the math, yes. But that's just for everyone. Everyone who defragments anything has to basically do writes and reads in order to move the data around.
No, but it can be now the algorithms when you do compaction on reads, right? I mean, write is just write, and read will do the compaction whenever it needs to be done.
If you do compactions on reads, you're not going to get large block optimizations, which are key for NAND. Further questions? Yes.
In terms of the implementation, MongoDB comparison to other databases, so MongoDB you have master, where you only write, and the replica which mostly for read. In Cassandra you have each node, in each node you can write. In the Aerospike, how is it?
How does our clustering system work? So remember I said we had sort of a micro-shard architecture. Ours is different from all, it turns out. So what happens is each one of those, what we call partitions, is mastered on one server, and then there's replicas that are randomly selected. And so what that means is, let's say you have a 5-node cluster. Each piece, each server is mastering 1/5 of the data. So it's smoothly allocated. So if you're writing, you have to write to the master first, which is essentially a transaction coordinator in Cassandra terms. So it's not actually a master, it's more of a transaction coordinator.
Isn't similar, you would say the design would be more similar to what Cassandra does, or what
Cassandra has the problem as a corded architecture. They have the replica is the next server in the core, whereas we do a random distribution. So with Cassandra, what happens is when you lose one node, the next node in the system becomes much hotter. In our system, if one node fails, it is the heat is randomly distributed throughout the cluster. All of the nodes become a little hotter. That turns out to be a real benefit in failure scenarios. So that random distribution of replicas and random distribution of transaction coordinators turns out to be a huge benefit, which is actually exactly what coherence does. So if you know Oracle's coherence product, we're probably most similar in clustering to them. So it's not master replica. Master replica is sort of a RAID 1 plus 0 kind of thing. We're closer to Cassandra, but we don't have the corded architecture. We have a random distribution. Any more questions? I'll come back to it. More questions? I see you got a question there.
Yeah.
I see you there. Your hand's going.
So that leads me to one. So actually, I was talking about on the site. Today I didn't see what I thought I'd seen in the past. It indicated immediate consistency or something near that, but it's always available. And if you've got the masters randomly distributed, then is that how you're able to try to resolve the conflict between those two aspects? I'm sorry if I'm not speaking it clearly. The propagation of new data.
Yeah, so it's sort of two questions. One is how do you deal with repair in the case of a split brain, which is a little different from the case of whether you have immediate consistency in terms of writes. So let me split those two things apart. Okay, so the default operation of Aerospike, when you do a write, it commits it essentially to RAM and the indexes and a buffering system on all of the servers in the replica set before returning a transaction complete message. This means you're never going to get a dirty read. During the transaction, of course, you're going to get different states depending on what server you talk to, but most people are going to talk to the master anyway for a variety of reasons. It's rarely optimal to ask other servers unless you have a very, very, very hot key. So in the case of that, since everyone tends to run with immediate consistency and write across the entire server, you don't get dirty reads. But that's still a case where the cluster is operational and it's not in split brain. So in the case of split brain and partition tolerance, what Aerospike does is it's an AP database today. We have some new engineering to also implement CP modes. And as an AP database, you want any part of the split to be able to take a write. So we accept that write. And the CAP theorem says if you're willing to take a partition tolerance and you want to stay available, you're going to have a conflict. Okay, so there you go, you've got a conflict. Aerospike's current system in conflict resolution, I would say, is underwhelming. We've got some work on board to improve some of that. We support one heuristic right now. It's not exactly last write wins. We found last write wins is not optimal in most cases because you end up having a split portion of the brain take a very small write, and then there's a very large object that is older but is actually more valuable. So the heuristic that most people choose in Aerospike is the greatest number of writes wins, as opposed to the most recent write. So that's what we have today in terms of actually healing the system after a split brain.
Is the winning decision favorable to the most recent write, or
Not yet. Not yet. I could go into what our plans are for all of that, but it's somewhat complicated.
so let me just make sure I understand this right. So for two reasons, it's going to have the appearance from the consumer that it's both A and C. In the case of a non-partition or without partition event, it's because there's
even if you read from the replica, you're going to get the correct answer, and you're not going to get a dirty read because it's right through to all of the replicas. Of course, if you read from a split brain, you're going to get out of date data, but that's the C problem of being an AP database. In the back.
When you say right through all references, is that just when you say right through all references, is that just for local data center or is that across?
Yeah, good question. It's only the local data center. So we don't yet have synchronous replication to the remote data centers, kind of for obvious reasons. So yeah, across data centers, it's always asynchronous, and thus the chance to have conflicting writes across data centers is high. And the first efforts that we have in greater conflict resolution will be in the cross data center system for doing things like distributed counters, distributed map data structures, etc., where you can easily resolve conflicts by simply doing merges, as well as having other user configurable systems.
Any other questions? All right, if a
talk
question comes up, Brian will be here for one-on-one questions right now. Thank you all for coming. Thank you, Brian Bulkowski.
Thanks for sticking around.